Well, what we're looking at here is a Tektronix 465M. This is the military, and in quotes, ruggedized version of the 465. 465 is probably one of the most popular analog scopes that Tektronix came out with in history, anyway. Still a lot of fans out there looking for it. The thing about the 465 is that, well, primarily it used a cooling fan, which was quite noisy and had a habit of going out. When they go out, then they'd cause problems. The 465M, on the other hand, doesn't use a cooling fan. It uses convection cooling and a rather large heatsink on the back. So it's noise-free. There isn't any air blowing around, and she's quite sturdy. And besides that, she's a very attractive unit. Nice features. 465 will measure frequencies from DC to beyond 100 megahertz at its 3 dB point. We'll test that on this unit and show that she's still in cal and that she's capable of achieving that bandwidth. It has a limiter switch that'll also reduce the frequency response to 20 megahertz to eliminate effects of high frequency when you're looking at mid-range. She'll read 5 millivolts per division to 5 volts per division, and she'll do it in 10 range steps using the vertical range switches. She'll do channel 1, channel 2 independently. It'll alternate between the two. You can add the two together, you can put it in chop mode, or you can run just channel 2 by itself. We'll demonstrate all of that in a little while. The intensity is quite good. We can go from very, very bright to completely off and then right back into between. We've got focus control, take us from a very, very soft blur down to sharp accuracy. We have auto mode, we have normal mode for triggering. Trigger adjustment, we've got single sweep. We can couple with AC, we can reject low frequencies or high frequencies, we can go with DC coupling. We can use channel 1, channel 2 as our source, either one. We can go off the line, we can put an external source on here. We can do XY. We can run channel 1 against channel 2. Okay, we're using our probe. We're going to the calibrator test point, and we're going to adjust ourselves for the best square wave. Alright, there's under, there's over, and right in between is the perfect position. Calibrator's working fine. We're still on times 10 too. That was another small slip up. Okay. If we wanted to adjust our trigger, we can take ourselves out of sync, into sync, out of sync, into sync. We're right now in auto. We can put ourselves in normal mode. If you're out of sync, you won't see a trace at all. Only when you're in normal mode. Auto mode, you'll see something all the time. You can put yourself on sync. Your trigger will trigger on channel 1. You can trigger on channel 2. You can trigger off the line voltage if you wanted. You can have an external trigger source. So you have various sources. We have AC coupling, DC coupling, You can adjust the position of the trace. If you don't know where the trace is and you want to make sure you have one, then there's your beam finder that you can hit. Our trace rotation and astigmatism have all been adjusted, but I'll demonstrate that the rotation works. Right now you'll see a level line. Alright, and if I adjust the rotation, you'll see that line tilt. See it? Go the other way, and then we'll level it out. Looks about perfect right there. This unit's in good shape. Has a decent cabinet to it. It's not scratch free. I wouldn't say anything like that. It's seen some battles, but it's in good shape, and it's in a nice shine to it. Nice finish. It's a handsome unit. I think anybody would be happy to have it. We're going to take it through its paces and just see how she performs. So bear with me while I set up, and we'll give it a try. Let's take a look at the underside too. Good shape. Very little in the way of scratches, and a nice shine. Nice sheen to it. Okay, I went to a little bit of extra trouble here, and I've taken the cover off and one of the inside covers, sheet metal covers, and I've exposed the insides here so you can get a good look at what the workmanship and technology and level of material is on this unit. It's really beautiful. Tektronix did a gorgeous job with this scope and scopes of its generation. It's what earned them the reputation. Vertical amplifiers. Beautiful. Alright, we're going to put her back together and get to testing it. Alright, we're gonna set this thing up on the shelf and make it a little easier for us to work on it. Now that we've had a little look at it. Okay, so we're set up right now to film the response. I've got myself plugged into a precision DC voltage source. We're using this Fluke 343A to provide our DC voltages, and we can dial up pretty much any voltage we want from 1,000 volts down to a microvolt. So pretty amazing unit. I am because of the noise level down at the microvolt level in particular, or anything millivolt level, we'll go there. I've got the probe set right now at ×10. So everything that I'm measuring at the scope end is 1/10 of what I actually have at the tip of the probe. So by doing that, I'm able to provide myself the voltages I need at the scope with less noise. because I'm actually providing something 10 times larger and then dividing it down. So just a little explanation as to what I'm doing here. Right at the moment we are putting in, it's a tenth of a volt at my fluke. We're dividing by 10, so we're really 0.01 volt at the scope, and we are right now on the 5 millivolts per division. There's our center gradical. We have 4 up and 4 divisions up, 4 divisions down. Right now we are exactly 2 divisions up, and that would be 10 millivolts. We have 10 millivolts coming into the unit, so that is correct. So let's go ahead and double that. We should see ourselves go full scale. And that's exactly what we did. We're right on the line at the full scale mark. Okay, so now I'm going to change my scale on the scope. I'm going to 10 millivolts per division. Well, we've got 10 millivolts, right now we've got 20 millivolts coming in. I am on the 10 millivolt per division scale. I am up 2 divisions, that's 20 millivolts. That's exactly what we want. So let's go ahead and raise ourselves. Here's 30. That went up 1 more division. Let's go to 40. We're full scale. It's exactly where we want to be. So let's change the scale on our scope. We're going to go to 20 millivolts per division. Well, we got 40 millivolts coming in. We got 20 millivolts per division. That means we're up 2 divisions, which is exactly where we're at. So let's go ahead and raise ourselves. There's 60. There's 80 millivolts. We're full scale again. On 20 millivolts per division, we are up 4 divisions. That's 80 millivolts. Okay, so then let's take ourselves to the next range is 50 millivolts per division. Well, at 50 millivolts per division, I'd have to be 100 millivolts up to be 2 divisions up. I'm slightly less than that because I have 80 coming in right now. So let's go to 100. Alright, 100 millivolts, and we are right on the line. Checking our scale. Right on the line. Right on the line. Perfect. Alright, so let's go to 0.2 volts. And we are at 50 millivolts per division. We're up 4 divisions. That's 0.2 volts. Alright. So we change our scale again. We go to 0.1 volts per division. Well, that'd be 0.1, 0.2 volts is 2 divisions up perfectly. That's exactly what it is. There's 3, 4. 0.4 volts would be full scale, which it is. So let's go to 0.2 volts per division on the scope, and we are up 2 divisions, so that's 0.4 volts. We have 0.4 volts coming in. That's beautiful. Now we're up to 0.8 volts, and we're full scale on the 0.5 volt per centimeter. So 0.2 volts per centimeter times 4 is 0.8 volts. 0.8 volts coming in. Beautiful. Alright, so let's change our scale again. We are now going to 1 volt per division. And if we want to be half scale, then we want 2 volts coming in. So in order to do that, I am going to take my times 10 divider off. I'm going to go times 1. And let's go 1. Alright, there's 1 volt per division. And we go up 2. So we're up half scale at 1 volt per division. That's 2 volts coming, 2 volts coming in. Take ourselves at full scale. Here's 3 volts, 4 volts, full scale. 2 volts per division, we're half scale. 5, 6, 7, 8. 8 volts per division, 8 volts full scale at 2 volts per division, 4 divisions, 8 volts. And that's perfect. Alright, so now we want to go change our range again. We're right now on 5 volts per division. So if we want to be 2 divisions above the half mark, that would be 10 volts that we would have to have. Alright, so here's 9, there's 10. 2 divisions up, 5 volts. Okay, we are at 10 volts coming in, we're at 5 volts per division, we're up 2 divisions, that's 10 volts. Okay. Okay, we're at 5 volts per division, we have 10 volts coming in, we're up 2 divisions. If we go to 20 volts coming in, we're full scale. That would be 4 times 5 is 20, 20 volts, no problem. So for DC, we are right on the money. It's perfectly calibrated. This is channel 1. Now let's quickly do a check for channel 2. Okay, we've got channel 2 connected up now. As we can see, the probe is coming into channel 2, and we now have channel 2 depressed, and what we're seeing on the screen right now is channel 2 with no signal applied. And now we're going to apply a signal. This will be 200 volts at 50 volts per division, and we jump up 1, 2, 3, 4 divisions, which 4 times 50 is 200 volts, and that's what we have. Let's take ourselves down to 100. That puts us at half scale, up 2 divisions. Good. Let's go to we want to go to 80 volts. There's 80, and we're going to go to 20 volts per division. That would be full scale. That's 80 volts. 4 times 20 is 80. And then if we drop down to 40 volts, there's half scale. Beautiful. Let's go to 10 volts per division. That puts us at full scale, 40 volts. Drop down to 20 volts. We're at half scale. That's what we want. And at 5 volts per division, we are at full scale. If we go to 10 volts in, we are at half scale. And so far, everything's great. Now we're going to go to we're on the 1 times probe now. Okay, we're on the 5 volt per division scale, and we're coming in with 10 volts, and we're up 2 divisions. That's great. Let's take ourselves to 2 volts per division, and we're going to go up to 8 volts. That should put us at full scale. Come back down to 4, half scale. Let's go to 1 volt per division. That puts us at full scale. Coming down to 2 puts us at half scale. 0.5 volts per division times 4 is 200, so that would be 2 volts. If we come down to 1, we're at half scale. Everything so far is great. So let's if I go to 0.2 volts per division, we want 0.8 volts coming in for full scale. There's 0.8 volts. Let's go to 0.2 volts per division. That's at full scale. Go down to 0.4. Puts us at half scale. We're now at 0.1 volt per division. There's 4 divisions up. That makes it 0.4 volts, and that's what we have. If we go to 0.2, we'll be at half scale. Beautiful. Alright, now we want 50 millivolts per division. Times 4 would be 200 millivolts. Let's check our 0. Looks like we drifted just a hair out. There, right on. Good. So we're at 200 millivolts at 50 millivolts per division. And if we go down to 100 millivolts, that puts us up 2 divisions. If I was to go to 80 millivolts, 80 millivolts at 20 millivolts per division, that puts us at 4 divisions up. If I drop down to 40 millivolts, we're at half scale. If I go to 10 millivolts per division, we're up 4 divisions. If I go down, if I drop my voltage coming in to 20 millivolts, I'm at half scale. If I go to 5 millivolts per division, I'm up to 4 times 5 is 20 millivolts, and I am at 20 millivolts right now. If I go down to 10 millivolts, I'm at half scale. So channel 2 tracked just as nicely as channel 1 did, and we are completely tracking the DC voltage and getting the proper response. So calibration wise for DC voltages, beautiful, huh? Okay, we're going to do some full and half scale checks for the AC, and bear with me while I set up, and we'll be right back.